Imagine calculations taking, well, not just decades, but septillions of years, done in minutes. It sounds completely like science fiction, right? Straight out of a movie. But today, that kind of fiction is becoming very real, tangible even. Welcome to the deep dive. Our mission today is to really get into Google's huge leaps in quantum computing. We're going to unpack the tech behind it, what this whole quantum supremacy thing actually means, how Google's tackling the really big challenges and what it all could mean for things like medicine, AI, maybe even your digital security. We want you to walk away with a clear, hopefully captivating understanding of this whole new frontier. Okay, so maybe for anyone needing a quick refresher, or maybe you're just tuning into this field, let's just briefly touch on what quantum computing is before we look at Google's work specifically. How is it so fundamentally different from, the computer on your desk?
Yeah, that's the crucial starting point. It's radically different. Think about classical bits in your laptop, your phone. They're always a 0 or a 1. That's it. Simple. But quantum bits, qubits, they're the game changer.
Yeah.
Because of this principle called superposition, a qubit can be a 0 and a 1 simultaneously, both at the same time. And this isn't just like a bit faster. Add one qubit, you double the states you can explore. It explodes computationally. It's possibilities that classical computers can't even touch. That's why it's a revolution, not just, an upgrade.
Okay, superposition. Got it. Both 0 and 1 at once.
Exactly. And then you've got entanglement. This is that sort of puzzling connection people talk about. Qubits get linked. Their fates are intertwined, even if they're miles apart. You measure one, you instantly know a state of the other. Instantly. It's bizarre, but true. And it's these two things together, superposition and entanglement, that let quantum computers look at loads of solutions all at once. That's how they perform these incredibly complex calculations so much faster.
Right. So qubits are the building blocks, superposition and entanglement are the weird quantum rules they follow. How do you actually control them, tell them what to do? Are there quantum gates, like the AND or gates we know?
You're exactly right. Just like classical computers have logic gates, quantum computers use quantum gates. These gates manipulate the qubit states. They're the basic tools. So one gate might nudge a qubit into that superposition state, that 0 and 1 state. Another one, like a CNOT gate, might entangle two qubits, creating that link. And when you string these gates together in sequence, you get a quantum circuit. That circuit performs the actual calculation, the operation you want to run, essential for doing anything useful.
Okay, makes sense. So we have the theory, the building blocks. When did Google first really show the world, look, this isn't just theory anymore? What was that big breakthrough moment?
Well, that's where Google has really been, leading the pack, demonstrating quantum supremacy. That term, John Preskill coined it. It means the point where a quantum computer can provably do something, solve a specific problem that even the best classical supercomputer practically can't. It's not about replacing your laptop. It's about showing a specific, undeniable quantum advantage.
A specific task where quantum just leaves classical in the dust.
Precisely. And Google hit that landmark first in 2019. They used their 53-qubit processor called Sycamore. It performed this really complex calculation, random circuit sampling, basically a very hard statistical problem designed to push these machines to their limit. Sycamore did it in 200 seconds.
Okay, 200 seconds. And the classical supercomputer?
The estimate was it would take the world's best supercomputer at the time about 10,000 years.
Wow, 10,000 years crunched down to just over 3 minutes. That's astonishing. But they didn't just declare victory and stop there, did they?
No, not at all. Progress has been rapid. By July 2023, they'd upgraded Sycamore to 70 qubits. And in a new experiment, this bigger processor tackled another, even harder computational task. It did it in under 5 minutes.
And the classical equivalent this time? Still thousands of years.
This time, the estimate for the fastest classical supercomputers was nearly 47 years.
Okay, so still a massive gap. 47 years versus 5 minutes.
A huge gap, showing that scaling up the qubits really was increasing the quantum advantage.
And then even more recently, end of 2024, this Willow Chip enters the picture. This seems to take the numbers into truly astronomical territory.
It really does. The claim with Willow is quite something. It supposedly solves a specific problem in 5 minutes. That would take the world's fastest supercomputers, wait for it, 10 septillion years.
10 septillion, that's a one with, 24 zeros after it?
That's the one, 10 billion years. I mean, just try to get your head around that number. It's vastly larger than the age of the universe. It's a scale of computation that's almost, beyond human intuition.
Right. 10 septillion years. That number alone, it really hammers home that this isn't just, some lab curiosity. It shows this exponential leap in what might be possible computationally. It's almost unimaginable. But playing devil's advocate for a second, these supremacy problems, like the random circuit sampling, are they actually useful problems? Or are they kind of designed specifically to make quantum computers look good?
That's a really important question. And, well, yes and no. These tasks are specifically designed to be incredibly hard for classical computers, but relatively manageable for quantum ones. So in that sense, they're benchmarks. They demonstrate the potential for that exponential speedup inherent in quantum mechanics. The big challenge now, the next phase really, is translating that raw power, the demonstrated potential, into solving problems that are not just hard, but also genuinely useful for science, for industry, for us. And that shift from benchmark problems to real-world applications brings us right into the major hurdles.
Okay, so what does all this mean for actually building a practical quantum computer, one that can solve those real-world problems? It sounds amazing, but what are the catches? It can't be that easy, surely.
Oh, absolutely not. There are huge challenges. This leads us to what you call the quantum quandary. The absolute biggest hurdle is something called quantum noise. See, quantum states, the superposition, the entanglement, they're incredibly fragile, delicate. Qubits are super sensitive to their environment, tiny vibrations, temperature fluctuations, stray magnetic fields. It all creates noise. This noise causes errors. It makes the qubits lose their quantum state. That's called decoherence. They basically forget the information they're holding. It makes reliable, long calculations incredibly difficult. It's like trying to build a complex sandcastle during an earthquake.
Right. The slightest disturbance messes everything up. So how is Google tackling that fragility?
Well, they've been making really significant strides. It's a huge focus. They use incredibly sophisticated calibration procedures, constantly tuning the system. And they use quantum error correcting codes. These are clever ways to encode the information across multiple physical qubits, so that even if one or two get noisy, you can still recover the correct information. And this is where the Willow Chip brought that massive breakthrough, something researchers have been chasing for nearly 30 years.
Okay, what was the breakthrough exactly?
For the first time, they managed to engineer and program the chip so that as they increased the number of qubits, the overall error rate across the whole system actually fell. It got better, not worse.
Hang on. Usually more complexity, more parts means more things can go wrong, right? More errors.
Exactly. That was the problem. Scaling up seemed to inevitably mean scaling up the errors too. But they found a way through the design and the error correction working together to overcome that.
So adding more qubits actually made the system more reliable, not less. That sounds counterintuitive, but huge.
It's absolutely huge. Hartmut Neven, who leads Google's quantum AI lab, he had a great analogy. He compared it to an airplane needing more engines for safety. Adding more engines doesn't make the plane less stable. If engineered right, it makes it more robust, more fault-tolerant. This is a really crucial step towards building truly fault-tolerant quantum computers, where you use many physical qubits, maybe dozens or hundreds working together just to create one stable, reliable, logical qubit. For instance, they showed they could make one logical qubit using 49 physical ones on Willow, and it performed better than any single physical qubit.
49 physical qubits just to make one usable logical one. That gives you a sense of the scale needed.
It really does. And while this breakthrough is massive, Google themselves are clear. The error rate still needs to drop much, much lower. We need to get those errors way down before we have machines that can solve really complex, widespread real-world problems reliably. There's this concept IBM pioneered called quantum volume, which tries to capture this. It's not just about the number of qubits, it's also about how well they're connected and, crucially, how low their error rates are. It's a more holistic measure.
Okay, so incredible progress on the error front, but still a way to go. Let's shift gears a bit. This isn't just about building faster calculators, right? It's about solving problems we couldn't even dream of tackling before. So beyond the tech specs, why should someone listening right now really care about all this? What's in it for, us?
That's the key question, isn't it? And first, it's important to manage expectations a little. Quantum computers are not going to replace your laptop or your phone for checking email or browsing the web. As Professor Alan Woodward put it, it's like comparing apples and oranges. They're not universally faster. They excel at a specific range of problems, particularly those that are inherently quantum mechanical in nature or involve massive combinatorial complexity. Problems tailor-made for them.
Okay, so not for everything, but for those specific problems, what kind of impact are we talking about?
Potentially revolutionary impact. Think about material science, designing new materials for, say, highly efficient solar cells, or room temperature superconductors, or even better batteries for electric cars. Quantum computers could simulate molecules and their interactions at an atomic level with incredible accuracy. We could essentially design materials atom by atom, or designing catalysts for cleaner industrial processes, maybe even understanding the mechanisms behind things like nitrogen fixation for fertilizers better.
Designing materials from the ground up. What about medicine?
Huge potential there, too. Pharmaceutical research, for instance. Simulating how a potential drug molecule interacts with proteins in the body is an incredibly complex quantum problem. Quantum computers could dramatically accelerate drug discovery, identifying promising candidates much, much faster than trial and error in the lab. Personalized medicine could also get a boost, tailoring treatments based on detailed molecular simulations of an individual's biology.
And fundamental science itself, like understanding the universe.
Absolutely. Subatomic physics, cosmology, modeling the interactions of fundamental particles, understanding the conditions of the early universe. These are areas where quantum simulations could provide insights we just can't get otherwise.
Okay, materials, medicine, physics. What about AI? That's the other huge tech revolution happening. Is there an overlap?
Definitely. There's a whole field emerging called quantum machine learning, or QML. Google even has its own open source framework for this called Circ. The idea is that quantum systems might be able to process and find patterns in huge data sets much more efficiently than classical algorithms. Think about optimizing complex systems, like training huge neural networks. Quantum approaches might find better solutions faster, or tasks involving pattern recognition in very high-dimensional spaces. Quantum algorithms might offer an advantage there. It's still early days, but very exciting.
Faster AI training, better pattern recognition.
And there are other areas too. Logistics, for example. Finding the absolute optimal route for, say, thousands of delivery trucks, or routing data packets through a complex network like the internet. These are optimization problems with a mind-boggling number of possible solutions. Quantum computers might be able to find the best answer much more effectively.
And then there's the flip side, security. I hear worries about quantum computers breaking encryption.
Yes. That's a major concern and a driver for research. Many of the encryption methods we rely on today, like RSA, which protects online banking and shopping, rely on the fact that factoring large numbers is incredibly hard for classical computers. But a powerful enough quantum computer running something called Shor's algorithm could theoretically break this type of encryption relatively easily.
So our current security could become obsolete.
Potentially, yes, which is why there's a huge global effort underway to develop new post-quantum or quantum-resistant cryptography. You mentioned Apple making iMessage quantum-proof. That's exactly what they're doing, upgrading to algorithms believed to be secure even against future quantum computers. It's a race to stay ahead.
Okay, so huge potential, but also some serious challenges and security implications to manage. Now, before we wrap this up, let's just quickly clear up something that made headlines a while back. Did Google's quantum computer actually create a wormhole, like a real sci-fi tunnel through space-time?
Yes, that story got a lot of attention. The short answer is no. Definitely not. What actually happened back in 2022 was a really interesting simulation. Researchers used Google's Sycamore processor to simulate a highly simplified mathematical model of a traversable wormhole. It was an experiment in quantum gravity theory, using the quantum computer to explore properties of quantum teleportation that mimic some theoretical aspects of wormholes. Think of it like using a flight simulator. You're simulating flying. You're not actually building a physical plane in the computer.
Right. So a fascinating physics simulation showing off the computer's power, not a literal gateway to another galaxy.
Exactly. It was about modeling complex quantum phenomena, not creating the phenomena itself.
Good to clear that up. So looking back at our conversation, we've journeyed from, well, science fiction concepts to actual tangible machines performing calculations that were unthinkable just years ago. It feels like we're truly at the dawn of a new era, even if practical, large-scale quantum computers for everyday, widespread use are still, well, probably years away, maybe towards the end of this decade.
That seems like a reasonable time frame for seeing more widespread, practical applications emerge, yes. The progress is accelerating, but building robust, fault-tolerant machines is still a massive engineering challenge. But these breakthroughs we've talked about, achieving supremacy, tackling error correction, they're absolutely fundamental milestones on that journey.
And it's not just Google, right? This is a global race.
Oh, completely. IBM, Intel, Microsoft, numerous startups, university labs all over the world. They're all pushing the boundaries. You see different approaches too, like the trapped ion qubits being developed at places like Oxford and Osaka universities, which some hope might even work at room temperature eventually. It's a diverse, competitive, and also collaborative global effort, which is really exciting to watch.
It really is. Okay, so to leave our listeners with something to think about. As this quantum technology keeps advancing, making things possible that seemed truly impossible before, what previously intractable problem in your own field, or maybe even just in life, might one day be cracked open by these incredible machines?